In this video, we're going to start to take a look at the formal definitions of limits as x goes off to infinity and to negative infinity. Before I do that, I want to just address the homework briefly. In these video lectures, we've worked with 4 specific types of functions. We worked with power functions, polynomials, rational functions, and algebraic functions. Okay. And in the homework, not every function that you encounter is one of those types of functions. That's not a mistake on my part. I didn't forget to lecture on other types of functions. What's happening is that the homework is pushing you a little bit. We may not have looked at exactly the type of functions that you're going to encounter in the homework, but the techniques that we applied to the functions that we did look at can also be used on other functions. So, focus on the techniques and the logic behind what we were doing, and you should be able to complete the homework. Now, I'm certainly happy to answer questions in office hours, but I don't want you to say, oh, wait, we didn't do one like this. This must be a mistake. It's not. Okay. So I've written up here on the board sort of our model definition. The basic one that we started with was the limit as x approaches a finite number of f of x being another finite number. Okay. And that was for every epsilon bigger than 0. Remember, that was a standard of closeness. That was our tolerance for the y values for how close we wanted f of x to get to this number L. And then we said there's going to be a delta bigger than 0. That was our tolerance or our standard of closeness for the x values. How close does x have to get to a? Such that if this inequality holds, this says that the distance between x and a is smaller than delta, so that x is close to a, using delta as our standard of closeness. This part just says that x isn't a. The distance between x and a is a positive distance. Okay. Then, this says the distance between f of x and L, so that would be the vertical distance between my limit and the y value on the graph, is smaller than epsilon, so that the y value is close to L using epsilon as our standard of closeness. Okay. So anytime we're writing a formal definition, it's going to basically model this. So if I'm saying the limit as x goes to infinity of f of x is L, and I've drawn a picture here of what that means. If x is going to infinity and we have a finite limit, that's saying we've got a horizontal asymptote at height L on the right side of our graph. Okay. So this will mean for every, and I'm just going to put some blanks where we've got to fill things in to modify this definition. For every blank, there's a blank. Such that if blank is true, then blank is true. Now, if we look here, f of x is still approaching a finite number. So the stuff that's describing what our y values are doing should be the same. What was describing what our y values did? Remember, we start and end talking about the y values. Okay. So those two bits are actually going to be the same. For every epsilon bigger than 0, that's going to be a standard of closeness for how close we want our y values to get to L. So that would be like, this would be here at L plus epsilon, this would be down here at L minus epsilon. And we're basically saying we want our y values to be within this horizontal strip so that they're within a distance of epsilon of what we're claiming the limit is, L. Okay. And, of course, that would mean that the absolute value of f of x minus L would be less than epsilon. I meant to do that in red. Okay, so the two blanks that talk about our y values are exactly the same. Now, the x values, that's going to be different because now x is going off to infinity. And you can't get close to infinity. So we're not going to have a standard of closeness for how close x gets to infinity. Okay. But if you think about what we did when we had infinite limits, where y was going off to infinity or negative infinity, there we were saying, hey, our y values are getting big. So we had a standard of bigness rather than a standard of closeness. Okay. So that's what we're going to have here as well. Okay. So we're saying x is getting big in the positive direction. So I'm going to introduce a number n, a positive number n, and that's basically going to be my standard of bigness. Okay. And what's it going to mean for x to be big then is that x will be bigger than n. So if we look at the picture here, we can see as we move to the right, it looks like right about here is where my function enters this strip that's close to L, within a distance epsilon of L, never to leave it again. Over here, it's in that same horizontal strip, but it leaves it and then comes back. Here, it enters and then it stays within epsilon of L. We're just going to say that that's our value n. So that if x is big, using n as our standard of bigness, so x is bigger than n, then my y values will be within that strip, within that range of values that's within epsilon of L. Okay. So we simply introduce a standard of bigness and say that x is big using that standard. Okay. Now, it is fairly standard to use epsilon as our standard of closeness for our y values and delta as our standard of closeness for x values. So you should be using those letters. That's considered standard. What letter you use as your standard of bigness, I'm less concerned about. Okay, I'm going to match the book. So I'm going to use n as my standard of bigness for x values. The book also uses m as the standard of closeness for y values. That's not quite as standard, so you're free to use whatever letter you use as long as you're saying, hey, I've got a positive number that's my standard for bigness. Okay. Now, how would this change if we changed this to be the limit as x was going to negative infinity? Well, first of all, the values that we're or the blanks that we're describing the y values wouldn't change at all. They're still getting close to L. Okay. But what would happen here is this would have to become a negative number. And instead of being bigger than n, x would have to be smaller than n. Now, obviously, that doesn't describe the behavior of that graph, but if I had a horizontal asymptote at L on the left side of my graph, I might have something like so, whereas x gets big in the negative direction, the y values are getting close to L. Okay. So, if you've got a standard of bigness in the positive direction, it's a positive number that x would have to be bigger than. If you've got a standard of bigness in the negative direction, it would be a negative number that x would simply have to be less than.